Hello Finxters! Today we will see a very interesting algorithm that builds on A-star search algorithm, namely the jump point search algorithm. The jump point search algorithm is optimized for path finding on grid maps, such as this one on the picture, for instance used in computer games. It exploits a property called path symmetry, which implies there is a path or path segments which share the same start and the goal vertex, have the same length and are otherwise identical but differ in scan order. The algorithm is fast, optimal and requires no memory overhead. It identifies and selectively expands only vertices of interest, which are called jump points. This means that vertices between any two jump points are not expanded, or in our familiar terms, they remained unexplored. This is a property that enables much faster algorithm operation by reducing the number of vertices that would otherwise have to be processed, an example by applying the original A-star algorithm. In our case, this grid map has edges between every two vertices, but I've omitted them from the picture to make it more clear. On the right side, there are a few symbols, some of which are already known from previous blogs, and some of them are new, so I'll try and explain them for you to be able to follow the rest of this blog. The first symbol is a scanned path, meaning it shows how far did the scan go in the algorithm. The visited path is a part of the path that points to the next jump point. The start vertex symbol, as usual, denotes a vertex which we use as a starting point for our algorithm. The obstacle vertex is a special kind of vertex that cannot be passed through. It presents sort of a wall for the algorithm. Unvisited vertex symbol means that it's actually an ordinary vertex we can visit and explore and use in a normal course of algorithm operation. The same goes for visited jump point and explored jump point, and finally the goal vertex here in the end or here on our grid map, which represents the final vertex which when encountered causes a termination of our algorithm. In the next slide we have a simple case, smaller grid. There will be a more complicated case a bit later, but right now let's start with a smaller grid and I'll show you how the search algorithm works. We are starting from this vertex 1, 1, and we are trying to find the vertex 1, 5. Between them is this vertex 1, 4. It represents an obstacle, a wall if you like. In real case, it represents a reason for why we cannot follow this straight path between our starting vertex and our goal vertex. The first step is to visit our starting vertex like this, and as usual we have prioritized it or queued it, put it in a priority queue, and now since we only have this one and only vertex in our priority queue, it will be the next one to be pulled out and explored. This is what we'll do in the next step. Now that we have explored the starting vertex, I should give you a few descriptions of what happened. The starting vertex actually scanned all of its immediate neighbors, so the first neighbors which surround it, and these are 0, 0, 0, 1, 0, 2, 1, 2, 2, 2, 2, 1, 2, 0, and 1, 0. These are all of its immediate neighbors. Now the question is, which vertices should be taken as jump points? Let's consider the first three: 0, 0, 1, 0, and 2, 0. 0, 0 leads to nowhere. It's the edge of our grid. It leads nowhere, so it won't be selected as a jump point. The same goes for vertex 1, 0, and the same goes for vertex 2, 0. 2, 0 is reached via a diagonal scan, and since we have no space to go on the left and down side, or purely on the left side, we will go straight down to 3, 0 and conclude that there is nothing here, so this branch is not of interest and it will not contain a jump point. The same goes for vertex 0, 1. It also leads to the grid point's edge, and it's also discarded as an interesting point. Similarly, for vertex 2, 1, we start a vertical scan from our starting vertex. We'll reach vertex 2, 1, and after that we'll reach the vertex 3, 1 and find nothing interesting, so there is nothing from this path to be recognized as a jump point. On this part, the situation is a bit different. While we go diagonally upwards from our start vertex, we find vertex 0, 2, and we could ask ourselves, what's so special about it? There is a rule in the algorithm that says if there is a diagonal move and there exists a vertex which lies on the path from this vertex, and this other vertex is a jump point, in our case that would be the vertex 0, 4, then 0, 2 is also a vertex. Maybe it's not so understandable what I'm talking about, but wait a moment and I'll show you what is it about. Just remember that vertex 0, 2 is a jump point only because its successor in the future, vertex 0, 4, is also a jump point. This applies only when we have a diagonal move. Okay. The same goes for vertex 2, 2. We make a diagonal move, then we go down and find nothing, and go right and find a future candidate for a jump point, that's vertex 2, 4, and because of that vertex, our scan, as indicated by this dashed line, dashed arrow, our scan currently finishes here in this iteration, and will declare vertex 2, 2 to be a jump point. Both of these jump points are added to our priority queue, and you can see them here as 0, 2 and 2, 2. Just let me explain what the elements of this tuple are. So the first element is the entity itself. It's 2, 2 and 0, 2 for our two cases. The second number represents the total cost of our vertex. I'll just back up to the previous slide to explain how to calculate this. We have the same value here and here for both of our jump points, and the last number indicates a direction in which the search goes. The directions are, you can look it up in the article: 0, going from a start vertex straight to the right, then 1, if we are going diagonally right and up, then 2, then 3, then 4 straight to the left, then 5 left and down, then 6 all the way, down, straight down, 7 down and right, and 0 once again. And whenever we pass this, let's imagine it's a border of direction 0. If we go from 7 to 1, let's say, directions go like 7, 0, 1. It's not like 7, 8, 9. There is not a direction named numbered with a number greater than 7. After 7 we have 0 once again. And if we go in the other direction, if we go from 1 to 0, the next one is 7. It's not -1 or something like that, it's 7. Okay, so let's return for a moment. I would just like to explain how to calculate the entire distance, the entire cost. So if we are looking at this vertex 5, 5, for instance, how far is it from the goal vertex? Its heuristic value, as denoted in the article, diagonally is 7 and 7 and 7, that's 21. And straight moves, meaning horizontal or vertical moves, cost 5 units, and that's entirely 7 plus 7, 14, plus 7, 21, plus 5, it's 26. So that's for the estimation part. Notice that the estimation can go over the obstacle vertices. It's only an estimation. And the second part of the entire cost of a vertex is the actual distance to the start vertex. This is something the algorithm calculates as it runs, so just bear in mind that there are two components of the total cost of a vertex. There is distance traveled so far, the cost so far in the source code from the start vertex to the vertex we are looking at, and there is also this other part, this heuristic value from the vertex we are looking at to the goal vertex. Is the same thing as in the A* search algorithm. Okay, so let's get back to where we stopped. We were right here. We recognized that vertices 0, 2 and 2, 2 are added to the priority queue, and the next thing is we should pull out of our priority queue the next vertex to explore. This will be the vertex 2, 2, as you can recognize is the first one. So let's do it. We are exploring vertex 2, 2. We have scan in the first, in the downwards direction. We have encountered vertex 3, 2, but it's not of interest to us. And now we have actually discovered a new jump point in the horizontal move, in the horizontal scan, and that's vertex 2, 4. So that's the reason why we are putting it to our priority queue. Now that we have scanned downwards or vertically and horizontally, we're making a diagonal move to vertex 3, 3, and after this diagonal move, 3, 3 is nothing interesting by itself. You can imagine we are continuing vertically down, but there is nothing to process, and there is also again a horizontal direction to the right, and there is also nothing interesting. So this iteration ends with the vertex 2, 4. Now let's explore the vertex 2, 4 and see where it leads us. By exploring vertex 2, 4, we are doing two things. The first thing is we are continuing to scan all the way to the right. There was nothing interesting. we stopped at the vertex 2, 7 because it represents an element of the edge of our grid map, so there's nothing interesting here. And there is one more thing interesting to remember and to note. We have actually added one additional course because we have a forced neighbor of 2, 4, and that's vertex 1, 5. Now that you look at all the neighbors of vertex 2, 4, these are 1, 3, 2, 3, 3, 3, already scanned. There was nothing interesting in them. 3, 4, 3, 5, also already scanned. 2, 5, also already scanned. 1, 4 is an obstacle, and besides this obstacle there is also this vertex 1, 5, which we recognized because we took a turn after an obstacle vertex. So now that we turned and added vertex 1, 5 to our priority queue, now let's do another more iteration. This time we'll be looking at vertex 1, 5. And when we explore vertex 1, 5, one of the first things to check in the algorithm is if this vertex we are exploring, is it a goal vertex? The algorithm found a positive answer to this question. It recognized vertex 1, 5 as our goal vertex, and it reconstructed the search path, and now we can see that our search path is 1, 1, 2, 2, 2, 4. Notice we've skipped this vertex 2, 3 because it was of no interest, so this is an improvement. Regarding the A-star algorithm, we skipped to the vertex 2, 4, and we have found the vertex 1, 5. Also, one thing to notice, we never explored vertex 0, 2, so that's a save in time, and we also never explored vertices 0, 5, 0, 6, 0, 7, 1, 6, 1, 7, and that's also a save in time. This is a simple example, so maybe it isn't so noticeable how is this algorithm making us any gains, but now you'll see in a less simple case how the algorithm works. Here we have a larger grid map with vertex 0, 0 as a starting vertex. We have vertex 1, 8 as the goal vertex, and we have three obstacles here, here, and here, and all the white vertices are vertices that are actually free to visit. They are available to visit, and now we'll see how cleverly the algorithm avoids most of these vertices. It doesn't process them, and how it finds the goal vertex very quickly. Let's start by visiting vertex 0, 0. As always, it is put to our priority queue, and the next thing to do is explore this. We will explore this vertex 0, 0. So in the next step, let's explore it. It gave us all the neighbors, all the available neighbors to scan. This is one specific thing about the starting vertex. It will always give you all of its neighbors because there are no restrictions on what it should and shouldn't give. There is no pruning in sense of in terminology of our algorithm, of the implementation. So the algorithm went all the way down. It found nothing interesting. It went to the right, and it stopped because vertex 0, 2 is an obstacle, so it cannot go any further. It also tried to go up, left, and in all other directions, but it wasn't possible because the vertex 0, 0 is on the edge, it cannot go any further on the left side and on the upside, but it also went diagonally to the left. It followed vertex in direction of 7, and it found vertex 1, 1. Why it recognized vertex 1, 1 as a jump point? Because later on vertex 2, 1 will be recognized as a jump point. It is queued, you can see it's put in the priority queue, and now let's go one step further. Now that we have explored vertex 1, 1, we have discovered, as I told you before, that vertex 2, 1 will be recognized as a jump point. So vertex 2, 1 is put into priority queue, and currently we have only vertex 2, 1 put into priority queue. You can also notice that vertex 2, 1 was reached by following direction 6, and you can also notice that its total cost is 49. Let's just try to calculate how did we come up with this 49. It's 7 in direction 7, it's 5 in direction 6, so 7 and 6 are 13. And now let's calculate the heuristic part. Remember the 13 on the side. It's 5, 10, 15, 20, 25, 30, 37. And its distance is 37 and 13. It should give 37 and 13, it should give 50, 49. Maybe I missed something somewhere, let me check. Yeah, I made an error when I was adding the two costs. So once again, this time in the correct order, the cost so far is 7 and 5. I said 7 and 6 before, I apologize, it's 7 and 5, that's 12. So let's go this way, it's 12 plus 5, 17, 22, 27, 32, 37, 42, and 7, that's 49. Okay, so now you know how to calculate the cost of a vertex when you're putting it to the priority queue. You'll always trying to go straight as far as you can and then diagonally to the goal vertex. Okay, let's go to the next one. Now we will be exploring vertex 2, 1. By exploring vertex 2, 1, we'll have a scan all the way down. We're always trying to continue the previous direction we came from, and as you can see for vertex 2, 1, that was direction 6, so all the way down. And also we've noticed there is an obstacle next to vertex 2, 1, and that also meant we have to make a turn and check if there is something interesting. There was vertex 3, 2, and we are using this vertex 3, 2, we are putting it to the priority queue, and we will explore it in the next iteration of the algorithm. Let's do that. Let's open the vertex 3, 2, and now we can see before we went diagonally left and down, and diagonally right and up. Diagonally right and down and diagonally right and up. We are always doing the scan horizontally and vertically. Vertically it would be all the way to the vertex 6, 2 is the edge vertex, so nothing happened here, nothing interesting found here. And horizontally we found vertex 3, 3, but we cannot go any further. There's an obstacle, so we are also stopping here. And when we are trying to see diagonally if there is anything interesting, we will discover vertices 2, 3 and 4, 3. First, let's ask ourselves, why do we have these two jump points? Maybe it seems a bit intimidating or complicating, but trust me, it's not. It's very easy. Now let's look at the available directions from vertex 3, 2. Why did we choose vertex 2, 3 to be our jump point? Because every time when we go diagonally, as we did from 3, 2 to 2, 3, remember, we are just exploring, we don't know anything yet. We are exploring, and now we are trying to go further diagonally from 2, 3. We are always trying to preserve our previous direction, but before we continue going diagonally, this is specifically important for diagonal movement. It doesn't apply to horizontal or vertical moves. Before we continue going diagonally, we have to check horizontally and vertically if there's anything interesting, and as we can see, horizontally we have an obstacle and we cannot go through it, so there is nothing interesting on the right, okay? But if we try going upwards, we can see that there is vertex 1, 3. Why is it interesting? Because it's next to an obstacle. And since vertex 1, 3 is next to an obstacle, it's a future jump point. And since it's a future jump point and it's coming from vertex 2, 3, 2, 3 is also our current jump point, and that's why we are marking it 2, 3 and adding it to the priority queue. The next thing to do is recognize why vertex 4, 3 is a jump point. Okay, so we made a movement from 3, 2 to 4, 3, and before we continue in our thoughts going diagonally to 5, 4 to 6, 5, we first have to check horizontally and vertically what's going on. So if we are going vertically down, you can always think of this diagonal movement as breaking on two parts. If it's going right and down, we will have two, let's call them check movements, one to the right and one to the down, the same one as we did with this one. We had a right and up, so there was an upward checking movement and to the right, but we were blocked. Okay, let's go back to this one. To check what is happening around vertex 4, 3, we are first going horizontally or vertically, doesn't matter. We are first going downwards and there is nothing going on here. The next thing to do is check to the right, and as we are checking on the right movement, we can also see there is this vertex 4, 4. It will be our next jump point. But since we didn't come to it yet, we will recognize that it will come from vertex 4, 3. So we are marking vertex 4, 3 to be our current jump point. Okay, let's see what happens next. We have our two jump points queued, that's 2, 3 and 4, 3. And the next one to be explored is the one with the highest priority or the cheapest one, and that's 2, 3, because its total cost, remember heuristic part plus the actual distance from the start vertex, summed together it's 53. Let's go with vertex 2, 3. And we are trying to go diagonally to preserve our direction. We couldn't do that. We couldn't do to the right a movement to the right, but we could do a movement upwards. And by this movement upwards, we have discovered vertex 1, 3. This is a jump point as foreseen earlier, because vertex 1, 3 is next to the vertex 1, 4. Let's go one step further. Let me check. You can always use the priority queue if you're not sure which one is the next one. It's 56. The cost is 56 for vertex 1, 3. So we'll explore vertex 1, 3. Let's go and do that. And what happens? Vertex 1, 3 will go in the same direction as it came from. It came from 2, 3 following direction 2. You can see in the article to remember which one direction, how is each direction numerated, but direction straight upwards is direction 2, and you can also check in the priority list. So there was nothing on the vertex 0, 3, it's not interesting, but since we had this obstacle vertex 1, 4, we also made a turn to that, and we also discovered jump point. It's vertex 0, 4. By putting vertex 0, 4 to our priority queue, we have only 2 jump points currently, and that's a vertex 4, 3, the cheapest one, and the vertex 0, 4, the most expensive one. The next one to go will be, judging by the priority queue, will be vertex 4, 3. It's this one. Let's do that. Let's explore it. And before continuing, remember, we are always trying to continue our previous direction. Before going diagonally, we're looking below it, and we found nothing interesting. We found a jump point right to it, because this jump point, this vertex 4, 4 is a jump point because it's right next to an obstacle. And after we scanned right, down and right, we are now free to proceed diagonally and check what is here. Is there anything interesting? From vertex 5, 4, we are looking down. There's nothing interesting. We are looking to the right, and once again, 5, 4 is not would not be declared a jump point by itself, because it's not near an obstacle, but its successor, vertex 5, 6, it will be a jump point. It will become a jump point in the next iteration. So because 5, 6 will become a jump point, its predecessor, vertex 5, 4, is also a jump point. So now currently we have vertices 4, 4, 5, 4 and 0, 4 in our priority queue. Let's check what's the next one to explore, and it's 4, 4. You can see it right here. Let's do that. And by exploring 4, 4, we are trying to preserve our direction of movement. It's to the right, but there's nothing here. There's only a vertex 4, 5 and an obstacle after it. So there's nothing here. But since 4, 4 is a jump point, it made a turn because it's next to an obstacle. We are turning from 4, 4 to 3, 5. And let's see why 3, 5 is an obstacle. Because 2, 5 is also next to an obstacle. Okay? But you can ask yourself, 3, 5, vertex 3, 5 is also next to an obstacle. Why couldn't it be declared a jump point just by itself? by disregarding vertex 2, 5? Well, the answer lies in the fact that if we would explore vertex 3, 5, as we will be exploring it in the next iteration, we couldn't make a turn to vertex 2, 6. That's also an obstacle. You see, you cannot make a connection between 3, 5 and 2, 6. 2, 6 would have to be a free vertex to declare vertex 3, 5 a jump point by itself. But it's not like that, so vertex 3, 5 is indirectly declared a jump point because its successor vertex 2, 5 will be a jump point. Okay, so let's do the next iteration. The next vertex to explore is vertex 3, 5. Let's do that, and by exploring it, we are confirming our previous finding that vertex 2, 5 is a jump point. We are adding 2, 5 to our priority queue, and now we have 2, 5 here, 5, 4 here, and 0, 4 here as our jump points. Let's see what should we explore next. The next one to go is vertex 2, 5, so is this one. Let's explore it and see what happens. Vertex 2, 5, as we explored it, produced 2 new jump points. One is vertex 1, 5, and the second one is vertex 1, 6. Okay, we already concluded that vertex 1, 6 is a jump point because it's next to the vertex 2, 6. And what about vertex 1, 5? Well, vertex 1, 5 is next to the vertex 1, 4, which is also an obstacle. So, in theory, with disregarding everything we have on our grid right now, we could assume that there would be a possibility for 1, 5, for vertex 1, 5 to turn to connect with vertex 0, 4. Will this happen or not? We'll see in a moment, but for now, let's just remember that vertex 1, 5 is a jump point because it's next to an obstacle, and in theory it could turn left and connect to 0, 4. Okay, we have 1, 5, 1, 6, 0, 4 and 5, 4. A lot of jump points for the moment, and let's check what will be our next jump point to process, to explore. It will be 1, 6. It has the lowest cost 60. Actually, it has the same cost as vertex 0, 4, but so it came to be that is the first one in priority queue. So let's go with it. Now that we are exploring vertex 1, 6, it tried to continue diagonally, but before continuing diagonally, it also had to check upwards. 0, 6 is not an interesting vertex. It tried to look to its right, and it found a vertex 1, 0. It still doesn't know it's the goal vertex. It just placed it in the priority queue because it was next to this vertex 2, 6, which is an obstacle. It also made a turn to vertex 2, 7, and because 2, 7 is also next to an obstacle, the same one, it also put it to the priority queue. And now what do we have? We have 2, 7, 1, 5 from before, 0, 4, 5, 4. Okay, so we have placed to the priority queue only 2 new vertices. Those are 1, 2 and 2, 7. Let's check which one should we explore next. that's 0, 4, and let's do that. Okay, something interesting happened. Let me go back and show you something. Here we can see that for reaching vertex 1, 5 from vertex 2, 5, if we go that way, vertex 1, 5 will have its total cost of 63. But we can also reach vertex 1, 5 by exploring vertex 0, 4. And if we go that way, its cost will drop. It's cheaper to reach vertex 1, 5 from vertex 0, 4 than it was from vertex 2, 5. It's cheaper, so actually vertex 1, 5 got disconnected from vertex 2, 5 and got connected to its new predecessor, and that's vertex 0, 4. So our path changed a bit, doesn't matter, it's natural to experience something like that, but just take notice that our vertex 1, 5 has dropped in its cost. It actually became the cheapest one alongside vertex 1, 8. Okay, and since it's the newest one to be added to the priority queue, it's on its top. Okay, so the next vertex to explore is vertex 1, 5. Just before we go further, I have to emphasize that by exploring vertex 0, 4, we try to, I'm repeating myself, but I'm trying to be clearer about it. Vertex 0, 4 tried to go diagonally up and right, but before that it tried to go right and it couldn't, up and it couldn't. It tried to go all the way to the right. It could, but it found this vertex 0, 8 and it stopped here because it's on the edge of our grid. And finally it turned around the obstacle and found this vertex 1, 5, which it, let's say, hijacked from vertex 2, 5. Okay, let's go to the next one. That would be vertex 1, 5. Let's explore that one. Okay, by exploring 1, 5, we actually didn't find anything new. Yeah, that's correct. So exploring vertex 1, 5 didn't bring us to any new discoveries. Let's go one step further. We will now process or explore, whichever term you like better, vertex 1, 8, and by doing that we will, actually the algorithm will, but also we will recognize that vertex 1, 8 is our goal vertex, and we will reconstruct our search path all the way to the beginning, and we will see that there is a way from vertex 0, 0 through 1, 1, 2, 1, 3, 2, 4, 3, 4, 4, 3, 5, 2, 5, 1, 6, and to the goal vertex 1, 8. This is our search path. On the other note, there is a possibility that there are two equivalent search paths, equivalent in terms of total cost, but it also can be one way or another. Either one of these paths can be selected. It's sometimes just let's say the order matters, because if you look at what we had here, we had, let's say, vertex 1, 5 with its cost 60 and vertex 1, 8 with its cost 60. If it turned out that vertex 1, 8 was on the beginning of our priority queue, it would be explored sooner than 1.5, and we would actually save some time but by not exploring vertex 1.5. But if you have multiple vertices with the same cost, it's actually in a way not determined which one will be explored first. It depends on how do you implement it. It actually also depends on whether you'll go when you explore the neighbors around the start node. Would you rather go clockwise or counterclockwise? There are some let's say decisions which don't actually impact the performance of the algorithm, but can impact the final path among the equivalent ones, which will be recognized as a path to the solution. This is all from me on this topic. I hope you managed to get a better feeling of how the jump point search algorithm works. I definitely recommend that you check out the source code. You'll get a much better feeling of how it works, how it can be implemented, how I implemented it. There are always better ways, different ways to do things, but you will definitely get a much better perspective on how it works if you check the source code and check the commentaries. I also commented the source code. I also try to do it as rich as I can to make it easier for you to understand how this stuff works. Okay, for this time, bye bye from me, and I'm looking forward to our next topic. Until the next time.